Okay, in the previous video, we have studied how to calculate the noise figure and the equivalent noise temperature for cascaded network. Now we are going to apply the analysis of cascaded network to study the noise analysis for a wireless receiver system. This wireless receiver system consists of a low noise amplifier at the input. This low noise amplifier is followed by a band pass filter, and this band pass filter is followed by a mixer. The low noise amplifier has an input signal SI and input noise NI, and it has again G amplifier equals 10 dB, and the noise figure for such low noise amplifier is 2 dB. And by the way, this value is very large. For conventional low noise amplifier, the noise figure is around or less than 0.5 dB, maybe 0.3 dB for example. This followed by a band pass filter. Band pass filter is a passive network, so it doesn't have a gain, it has a loss factor. So the loss factor for the band pass filter is 1 dB, means that the output power is less than the input power by 1 dB. Here the output power is greater than the input power by 10 dB. This band pass filter is followed by a mixer, and we have something called conversion loss. When we are converting the signal from frequency to another frequency by using a mixer, the amplitude of the output signal or the digital signal will be less than the amplitude of the input signal. So we have mixer loss, and the mixer loss in this case LM is 3 dB, and the noise figure for the mixer is 4 dB. And actually the mixer is a good example for a noisy circuit in the wireless receiver system. So we have a large noise figure here. If we remember, for a lossy network, the noise figure equal the loss factor. So I have not mentioned the noise figure here because effectively can be obtained directly. The noise figure for this band pass filter, it will be 1 dB. Alright, and the output is coming from the mixer, so the output, it would be the output signal is S naught and the output noise is N naught. It is assumed that the IF bandwidth of the band pass filter is 10 MHz. So this is actually the bandwidth of this receiver system. We are assuming that this receiver is connected to an antenna, a receiving antenna, and the equivalent noise temperature for this antenna is T antenna is 150 Kelvin. So the input noise temperature, the input noise is kTA multiplied by D. TA is 150 Kelvin and D is the bandwidth, which is 10 megahertz, 10 multiplied by 10 to the power 6. At the beginning, we are going to convert all the dB values to ratios. So the value of the gain 10 dB, as a ratio it would be 10. The noise figure of the amplifier FA 2 dB, as a ratio it would be 10 to the power 2 over 10, which is 1.58. On the other hand, the gain for the band pass filter is minus the loss factor, so the gain is minus 1 dB. As again, it would be, as a ratio, it would be 10 to the power 0.1, minus 0.1, 10 to the power minus 0.1. 10 to the power minus 0.1, it would be 0.79. On the other hand, the noise figure, it would be 1 dB. So the noise figure for the filter, it would be 10 to the power zero point 0.1. Here 10 to the power minus zero point 0.1. Here is 10 to the power zero point 0.1. So it would be 1.26. Finally, the gain for the mixer would be minus 3 dB. In terms of the ratio, it would be 10 to the power minus zero point 0.3, which is 0.5. On the other hand, uh, the noise figure, and it should be noted here that the noise figure here, uh, it does not equal the attenuation coefficient. It is greater than the attenuation coefficient. Because inside the mixer, we have thermal noise and flicker noise and other types of noise. So effectively, the noise figure is greater than the loss factor. So the noise figure would be 4 dB. As a ratio, it would be 10 to the power zero point 0.4. It would be 2.51. Now, from these quantities as ratios, we can say that, okay, the total noise figure for this system, it would be the noise figure of the amplifier FA plus the noise figure of the bandpass filter minus 1 over the gain of the amplifier GA, which was G1, plus the noise figure of the mixer minus 1 over the gain of the amplifier multiplied by the gain of the filter. So by taking these values, FA is 1.58. Should be noted here that this equation is based on the ratios, not on the dB. So it would be 1.58 plus 1.26 minus 1 over the gain GA 10, and here 10 is a ratio, not dB, plus FM, which is the third one, 2.51 minus 1 over the gain of the amplifier GA 10 multiplied by the gain of the filter, which is 0.79. Now, by taking the summation of these three terms, we can find out the total noise figure is 1.8. In terms of dB, it would be 10 log 1.8, which is 2.55 dB. It is interesting to note that the total noise figure is slightly greater than the noise figure of the low noise amplifier, and is actually less than the total noise figure or the noise figure of the mixer, for example, which is 4 dB. This means that the noise figure of the low noise amplifier determines the total or the overall noise figure of the receiver system. And if we increase the gain here, instead of 10 dB, for example, 20 dB, so instead of 10 it would be 100, we will find that this would be more closer or closer to the value of 2 or the noise figure of the low noise amplifier. So effectively, to design a microwave receiver, it is required to increase the gain of the low noise amplifier and to reduce the noise figure of this low noise amplifier, such that the total noise figure of the system, it would be such a small noise figure. Now, we have determined the noise figure of all this system. The question now, what would be the output noise if this receiver is connected to an antenna with a noise temperature 150 Kelvin? So in this case, the input noise, it would be K multiplied by the noise temperature of the antenna multiplied by the bandwidth, which is 10 megahertz. So this is the input noise. The output noise, it can be determined in terms of the noise figure and the input noise. Or in other words, we can determine the equivalent the total equivalent noise temperature for this system is the noise figure minus 1 multiplied by T naught. And T naught here is the room temperature, which is 290 degrees. 290 degrees Kelvin. So we already calculated the noise figure as a ratio 1.8. So the equivalent noise temperature for this receiver would be 1.8 minus 1 multiplied by 290. It would be 232 Kelvin. Now the total noise due to the input plus the internal noise, it would be the total noise in output. It would be the total gain multiplied by the bandwidth multiplied by K multiplied by the equivalent noise temperature inside the circuit plus the noise temperature from the antenna. So the value GBK multiplied by TA is effectively the input noise multiplied by the gain of the total system. In addition, G multiplied by K multiplied by B multiplied by TE is the internal noise coming from the receiver. So the total output noise, it would be G multiplied by KB multiplied by T antenna plus the internal equivalent internal temperature. The value of K is Boltzmann constant is 1.38 multiplied by 10 to the power minus 23. The noise temperature for the antenna is 150. The noise temperature or the equivalent noise temperature for the total receiver is 232. The value of the bandwidth is 10 gigahertz, 10 multiplied by 10 to the power 6. And the total gain here is the gain of the amplifier multiplied by the gain of the filter multiplied by the gain of the mixer. The gain of the amplifier is 10 multiplied by the gain of the filter is 0.79 multiplied by the gain of the mixer is 0.5. So the multiplication 10 multiplied by 0.7 multiplied by 0.5 is 3.95. So this is the total gain of this system. Now by calculating this, we can obtain the output noise. The output noise in this case, it would be 2.03 multiplied by 10 to the power minus 13 watt. If we divide it by 1 milliwatt and taking 10 log of this value, we can represent this noise in terms of dBm. As dBm, it is minus 96.8. So we are going to divide this by 10 to the power minus 3 and taking 10 log of this value, we can find the output noise in dBm is minus 96.8 dBm. This is the output noise here. The question now, if this is the output noise and this receiver system requires that the output signal to the output noise, it should be around 100 dB. What would be the required input signal as the input here? So assuming that if the output signal to noise ratio is required to be 20 dB, for example, what will be the required input signal here? What is the input power here? To determine the input signal here, okay, here we have already calculated the output noise. So the output noise is 2.08 multiplied by 10 to the power minus 13. And it is required that the signal to the noise ratio is 20 dB, which is equivalent as a ratio 100. So this means that the output signal should be this value multiplied by 100. So the required signal S naught, it should be 2.08 multiplied by 10 to the power minus 11. This output signal is effectively the gain multiplied by the input signal. So if we divided the output signal by the value of the gain, the total gain, which is the gain of the amplifier multiplied by the gain of the filter multiplied by the gain of the mixer. So the input signal, the required input signal, S input, it would be the output signal over the value of the gain. And as I said, the output signal, it would be 100 multiplied by the value of the noise over the total gain. So this would be 100 multiplied by 2.08 multiplied by 10 to the power minus 13 over the total gain 3.95. So the required input signal such that the output signal to noise ratio is 100 dB, it should be 5.27 multiplied by 10 to the power minus 12 watt. In terms of dBm, we are going to divide this value by 10 to the power minus 3 and taking 10 log of this value. So the input signal in dBm, or the required input signal in dBm, is minus 82.8 dBm. This signal is the required signal such that the output signal to noise ratio would be 100, or in terms of dB, it would be 20 dB. This is the signal in dBm. The question, what will be the magnitude of the signal, or the voltage of the signal in this case, assuming that the input port here has a characteristic impedance 50 ohm. So effectively, this is the input power, and this input power can be represented as V squared over R. So if I have the power, I can obtain the input voltage, or the required input voltage. So for a 50 ohm system, assuming that the characteristic impedance is 50 ohm, we can say that the input signal, S input, is V squared over 50. Or in other words, we can say that the input voltage, V input, is the square root of Z naught, which is 50 ohm, multiplied by the input power signal SI. So if the value of the input power is 5.27 multiplied by 10 to the power minus 12 watt, I'm going to multiply it by 50 and taking the square root of this value. So we can find out the required input voltage of the signal. It would be 1.6 multiplied by 10 to the power minus 5 volt, or in other words, we can multiply this by 10. It would be 16.2 microvolt root mean square. So this is the input voltage at the input here to obtain a signal to noise ratio 20 dB, or in ratio 100. Okay. Now we have the input signal, and effectively we have the input noise. The input noise is K multiplied by the temperature of the antenna equivalent temperature multiplied by the bandwidth. What will be the situation if we try to calculate the output signal to noise ratio, or the output noise, from the noise figure? As we said that before, the noise figure is defined as F equals the signal input to the noise input over the signal output over the noise output. So we already have the total noise figure for the system, which was 2.55 dB. If I remember, we said that the total noise figure is 2.55 dB, or in ratio it is 1.8. So I have the noise figure, and already I have the input signal and I have uh, the input noise, and I know the required output signal. I said that the required output signal is 100 times of this value. So the required output signal is output is 2.08 multiplied by 10 to the power minus 11, assuming that I have multiplied by 10 watt. So I have this output signal, I have the input signal, I have the input noise. So let us calculate the output noise. If we do this, we find that, okay, if the noise figure is 2.55 dB, or in ratios it is 1.8, we can say, okay, the output noise is the input noise multiplied by the noise figure multiplied by the output signal or the output power over the input power. This is actually coming from the definition here. Here we say that the noise figure equals the signal input over noise input over signal output over noise output. So we can arrange it as follows. Noise output over noise input multiplied by signal input over signal output. This is signal input equals F. So I can say that, okay, the output noise is F multiplied by signal output over signal input multiplied by noise input, which is this one. Noise output is noise input multiplied by F multiplied by signal output over signal in. Okay. Noise input is K multiplied by the noise temperature of the antenna multiplied by the bandwidth. This is the input noise. F is the noise figure. The magnitude of the output signal to the input signal is effectively the gain. So let us calculate this. K is Boltzmann constant. Noise temperature of the antenna is 150. The bandwidth is 10 megahertz. Noise figure is 1.8. And the gain is 3.95. If we calculate this, we find that the output noise is 1.47 multiplied by 10 to the power minus 13 watt. Actually, this is not the same value as the output noise which we have started with. What is wrong? What is wrong? Effectively, the wrong here is that what is the definition of the noise figure? If we return back to the definition of the noise figure, we said that in the definition of the noise figure is the signal to noise ratio at the input to the signal to noise ratio at the output, assuming that the input is at room temperature. So, assuming that the resistance of the noise at the input has an equivalent temperature 290 Kelvin. But actually, in the present case, the input noise is coming from the temperature of the antenna, which is 150 Kelvin. So effectively, using the noise figure to calculate the output noise here is completely wrong. Why? Because the input signal is not at room temperature, or the equivalent noise temperature is not the room temperature. This is the source of the error in this case. So in this case, we say that this is incorrect result, and the reason here appears because that the definition of the noise figure assumes that the input noise level is KT naught B, not KT antenna B. And T naught is fixed value, 290 Kelvin. So the problem here involves with inputs noise KTAB, not KT naught B. And the value of the noise temperature of the antenna is only 150 Kelvin, which does not equal T naught. So effectively, this is a common mistake in calculating the output noise by using the noise figure. So instead of using noise figure to be in the safe side, use the equivalent noise temperature. So this is a common error, and suggests that when computing the absolute output noise power, it is often safer to use the noise temperature instead of the noise figure, especially for a cascaded system. Okay? Alright. Now we have completed the example for noise analysis of wireless receiver system. In the following video, we are going to talk about what will be the noise figure for passive two-port network instead of using active network, including amplifier, including positive gain or gain greater than unity. What will be the situation if it is passive two-port network? How to calculate the noise figure in this case? This is what we will see in the following video. Alright? Okay.